So just again, thanks, Kushal, for the intro. Yes, Eric here. I'm a director at Tenstorrent. Tenstorrent's a Toronto-based startup. Toronto right now has about 5 inches of snow. I assume some of you are experiencing the same as what I am. And as Kushal mentioned, yes, we're producing microprocessors tailored specifically for ML workloads. And we've been in business for about 5 years, and we're starting to make some significant waves in the performance AI compute space. And I would say that my company is a new sponsor for TMLS. So thanks again to Dave and to Kushal and to the TMLS team for the opportunity to speak today. And just a comment, I am full screen, so I'm not able to see any questions right now, but I will address them at the end through Kushal. So just to kick off here, you've probably all heard of Moore's Law, or at least you've heard of it. Gordon Moore is a former UC Berkeley prof. He founded Intel in the 60s, and he famously stated that the number of transistors on a microprocessor will double every 2 years, thanks in large part to transistor shrinkage. The idea being that if you can squeeze more transistors on a die, the relative performance will go up. So I think at this stage, that's pretty common knowledge. And you probably also heard it said that Moore's Law is either dead or dying, due in part, in fact, that transistors are now being produced at nanometer scales where quantum effects, for instance, will prevent physical barriers to further shrinkage. And this guy said it, CEO of NVIDIA, David Patterson, particularly relevant because he's a prof at UC Berkeley where Gordon Moore himself was. And this is something I was taught in my undergrad, my comp sci undergrad. We were told that Moore's Law is reaching its plateau. But interestingly, not everybody agrees. This guy here is Jim Keller. He's an industry veteran with over 40 years experience, pretty smart guy in a position to know what he's talking about. He was the original author of the x86-64 instruction set in the 90s, co-authored that. If you ever had an iPhone 4, he was the one that you used one of Jim's chips in the past. He was the producer of the very first Tesla automotive chip for autonomous driving. And up until quite recently, he was the SVP of engineering at Intel. And at Intel, he famously gave a speech entitled, "Moore's Law is not dead, and anybody who thinks so is an idiot." So it's pretty controversial, obviously flies in the face of my presentation, which is kind of interesting considering he's now president and CTO of Tenstorrent. He's my boss. So here's the alternate title for my presentation. Career Limiting Moves 101, Contradicting Your Rockstar CTO. And honestly, if I'm being serious, the thing is he's probably right. And regarding Moore's Law, you should trust him over me. And I'm not just saying that because I like my job, which I do, but he's been designing computers since before I was born. And he's got the stats to show the processors are still increasing in performance at a relatively consistent and predictable rate. And certainly you can look up the video and see the case he made on YouTube. The trouble is in AI, it actually doesn't matter. And this is what I want to look at here. So you see on the left-hand axis here, we have an exponential growth. And on the right-hand side, we've got time. And what we see here, and I appreciate the colors are a little hard to see. We have a gradient, which is representing the exponential growth of Moore's Law. And we have an even steeper gradient here, which is the doubling of ML compute demand, if you like to look at it. And if you're familiar with the generic pre-trained transformer, GPT-3 would probably sit somewhere around here. Now, the message here is the computational demands of machine learning tasks are increasing exponentially. And with processor speedups increasing on a much lower exponential, we're on a fast track to computational demand outpacing supply. And in fact, it's already happening. So one of our partners, Lambda Labs, has produced research that said for GPT-3 that I just referenced, on an NVIDIA A100 instance, it would take 350 years and cost $5 million to train. So obviously, this is not super democratizable. This is not the kind of thing that a citizen machine learning engineer or a small organization could bite off and chew. So as an industry, we got to think of novel ways about dealing with the demanding workloads that are coming down the pipe both on the software optimization side. We've got some interesting presentations today around software, software optimization, but also on the hardware side. And so this is what my team at Tenstorrent is working on. We've built technology which features things such hardware acceleration features such as conditional execution, dynamic graph sparsification, early exits. And what I want to do today is take a look at sparsity and how that can be leveraged to speed up processing in particular. Now, for a lot of the maths and science undergrads, you'll have some background on graph sparsity, but for the uninitiated, I drew a picture of a dog. So coincidentally, this is also my response to any questions about, so Eric, why don't you have an arts degree? This is why. Now, here's that same dog drawn in binary, and if you pull away a little bit and squint, I think you can probably just about make it out. So in a typical AI process, you're going to take blocks of this image, you're going to do feature detection for pre-assigned lines and shapes, you're going to iterate across the entire image looking for areas of interest and the features that you've defined. And you have, in your training, you've labeled these effectively, and you get a classification. So in my classification here, it's low probability human, maybe it's a goat, maybe it's a horse, but pretty sure it's a dog. I'm definitely sure it's a terrible, terrible drawn dog. But within the neural network, in the underlying computation side, this is represented by a series of matrix multiplications. So various weights and activation neurons. And this is done at each node and each layer across the graph. So you're looking at this times this, plus this times this, going through the entire thing, plus this times this. It's a lot of volume, and that's computer vision in 30 seconds. But this means, as I said, as the training volumes and the input sequences increase, these matrices expand outwards on a quadratic basis, on an exponential basis, rather. So new nodes, new weights means more matmuls, more computation on an exponential basis. And this is a good chunk of the reason why we're actually seeing that exponential growth in the model processing time. Bigger models take exponentially longer. So going back to that picture of the dog, there was a ton of white space in that image. You might even say it's kind of sparse. So would it make more sense to ignore the white space that obviously isn't part of the dog image? I mean, if 95% plus of your processing time is looking at white space, isn't that a huge waste of time? And of course, time in computation is money as well, and it's an expensive process. So good point. Let's have a look at this quick video while I take a swig of water. Don't worry, there's no sound. This is just something I found on Reddit that I thought illustrated a point pretty well. So we learned in school that any multiplication where a factor is 0, the result's 0. But we know that computers don't have that intuition. Their computers are going to naively perform all the jobs you give it, whether or not it's actually contributing to the end result set. So wouldn't it be cool if we could proactively eliminate the calculations that aren't going to contribute to our end result? I think so, and this is effectively what we're doing. By taking advantage of sparsity, we can really significantly lower the volume of computation. And combining that with high performance chips, you can see significant upticks. I'll show you what that looks like. It's actually possible to remove large sections of neural nets without impacting accuracy. If you're thinking about this and thinking, oh, okay, yeah, but if you're going to if you're going to sparsify a net, then it's going to have, big impacts on the accuracy of the classification. Actually, there's a lot of interesting research that's been published in the last couple of years that shows that's simply not the case. And in our tests, we're seeing, fairly negligible impacts to accuracy. And feel free to Google this. You'll find lots of independent white papers on graph sparsity and how this can be leveraged. In fact, there's one researcher called Vivian Z from MIT who has written a couple of really interesting articles. So feel free to have a read of those. And I should say, although this is kind of a silly example, this sparse dog, The same broad theory applies to color images, to natural language, to recommendation systems, pretty much anything that can be represented by a neural network or in a deep learning process. So we took this thinking into our chip architecture, and we designed a chip that can dynamically induce sparsity in both training and inference, so that training being a key point here, we can do both training and inferencing modes at runtime. And I think the results speak for themselves. Compared to this market leader, we're a significant reduction in cost, let's say a tenth of the cost, a quarter of the power, but we're seeing, comparable, if not better, results in terms of throughput. And in some cases, we're seeing quite substantial increases in throughput, but noting that there is additional memory on board to support recommender systems. So beyond being good at doing things like sparsity and conditional execution, we wanted to make this something that would be actually useful to the community. We're not the first organization in the world to produce an AI chip. However, other organizations, have stumbled a little bit when it comes to developing proprietary ML frameworks. We really didn't want to do that. We wanted to go where the community was heading with these things. We see this as being most easy to adopt if it can already natively compile PyTorch code, for instance, or other ML languages you're familiar with. So we developed our own native graph compiler, which is seen here in this purple box, for PyTorch and for Onyx, meaning that your existing models will work right out of the box without the need for refactoring code. And we can also run other frameworks directly through this Onyx path. Onyx is the Open Neural Network Exchange, which is a nice framework for porting in other model types like TensorFlow, etc. So I thought I would give you a quick peek under the hood here. Let me think about how I should talk about this. So I should note that being good at map models isn't the whole story, obviously. We've got big memory arrays on chip. So along the edges here, you're seeing banks of, this is DDR4 RAM, each a gigabyte of memory, which is useful for loading interim states, this kind of a thing. You'll see these blue T's. These are Tensix cores, which is our proprietary core. Each of these cores contains 5 RISC-V cores inside it. It has a megabase SRAM as well. We're also useful for small data storage. And we take a packet view of the world, which is kind of an interesting feature, because what that means is we can do things like variable input sequence lengths, right? So we could have a set of cores that are allocated to one model type, which receives variable input sequences, and perhaps another set of cores that are dedicated to another type. So you could have, multiple models running on the same chip and performing really well. So yeah, 5 RISC-V per Tensix core. This is a 10 by 12 array of Tensix cores in this what we call our Grayskull chip. So that's what it's a lot of computing power. And this is a very modular and dynamic architecture as well. The next generation of our chip, Wormhole, which is coming out early 2022, is fundamentally the same architecture. We still have rows and columns of these Tensix cores, but what we're going to be adding is Ethernet ports around the edge of the chip as well. Ethernet on chip, which will do interesting things, allowing us to network these within a data center for really large implementations. So the idea here being we could have arrays of tens of thousands of these chips working together for really massive compute. This Grayskull sits on a PCIe bus, so it comes on a board which would fit into a standard motherboard or rack system. And that's kind of what you see in this picture here. That's the vision. So you have multiple of these systems working together. And yeah, so we'll also enable things like early exits, which I kind of mentioned earlier. If you wanted to stop inferencing after a model reaches a certain level of confidence, you could do that as well in the hardware layer, which is useful features. So the other part I kind of high level touched on is around scaling. So scaling can be a big challenge. We're thinking it would be really cool to be able to train a model on a data center cluster and then use that trained model on to inference on the edge without having to worry about cross compilation. And this is very applicable in autonomous vehicle situations where they might be training on a high performance compute data center with a different high performance uh, AI compute card, and then having to use a smaller different model in their vehicles for inferencing, and usually that's driven by things like power constraints and others. So for the embedded edge, we're looking at several deployments because our chips actually run in a relatively low power envelope of 75 watts. We're looking at smaller envelopes as well, but also within that same chip can be used in parallel together to build really, really high performance systems. So as I mentioned, we could build these into systems and racks, and you can have a lot of compute power on-prem or off-prem and in a co-location very, very quickly and at relatively low cost. The other point I want to drive out here. So the other nice aspect about designing specifically for the ML community is that we're not bundling more than what you need. I mean, if you buy a GPU, you might be paying for a lot of technologies that you may never use. I was telling Kushal today, like I'm buying a car and I'm buying a car today. And one of the things I was doing was eliminating things from my list of things that I will never use, right, to drive down my purchase cost. And I think there's kind of an analogous thing here as well. If 99% of your work is focused on ML compute and you're using a GPU which has a lot of onboard functionality for graphics processing, that's a lot of additional functionality that you're paying for that is being unused. We're not bundling that stuff. We're really focused on ML compute specifically. And what I wanted to do here was show a few examples of the types of models that we've tested on our system. I flashed up that performance slide earlier, which addressed, we're looking at, we've done some tests on NLP systems, on vision systems, and recommender systems. Here's a deeper dive look at some of the models that we've actually run and have real performance on. But honestly, I think the real opportunities here are for the community to train and operationalize really large-scale applications using our technology. And at the same time, we're hearing need for performance in the edge. We're having conversations with some organizations who are doing things like integrating vision systems into point of sales terminals, right? That's a really interesting application, and certainly that's something we can deliver on. But we think the real innovation on this is going to come from the users of our chips, right? So while the ML community is focused on delivering and building really high performance ML applications, we're going to be spending our time focused on building very high performance ML processing technology fundamentally to make your job easier and allow you to do more interesting stuff, research and publish faster for the academics, but also deliver more experimentation in potentially retail scenarios and try out some different things and experiment more and see what you can get out of it. So I will leave it there. That's me been speaking for a few minutes now. I'm going to close my share, and if anybody has any questions, I will be happy to address them now. And I should also mention that I will be jumping into our booth after this, and I can have any conversations that anybody might like to have. Be happy to jump in.
Thanks, Eric, for the great presentation. So we have a question. Does it run models written in JAX?
So my answer to this would be, if it can be for all can it run models written in X language, as long as it can be exported in an ONNX format, the answer is yes, it can be run. And typically, your IDEs will be able to deliver an ONNX output, no problem. So Tianle, I hope that answers your question.
So I think so. We have no more questions. So anything else you would like to add, Eric?
No, but I would like to say to you, thank you again, Kushal, for the intro, and to everybody else, very happy to connect with you in our booth, and feel free to send me a note over LinkedIn if you'd like to connect offline. That's totally okay as well. I think my LinkedIn details are shared on the presenter page, so you should be able to find me there. And yep, happy to have conversations about evaluations, about you know trying out Tenstorrent hardware, seeing how it compares to your existing architecture. Certainly interesting, exciting, and engaging in all kinds of different modes. So feel free to send me a message.
All right. Thank you so much, Eric. It was a great
Thanks, Prashant.
presentation. All right. Have a
Cheers.
good day.
Take care. You too.
Take care. Thank you, everyone.